I'm Will Steinhardt. I'm a postdoc at UC Santa Cruz, working with Emily Brodsky. And today I'm going to tell you about some of my sort of non-traditional experiments, our sort of unique lab fault where we're using rubber to try to understand earthquakes, and the ways in which we can use that system almost like a sort of numerical model, but in a physical system, so a physical fault model. I just noticed there's a chat. Okay, great. Okay, so there is, as Sylvain said in his intro, there's these range of geophysical systems that I'm interested in that are predominantly stable, but then become unstable catastrophically with these severe societal consequences when they do. And these systems, in general, are kind of hard to predict for a number of reasons. So first is they involve really extreme spatio-temporal scales. Right, they're accumulating stresses over decades or even centuries, but they're nucleating failure processes in fractions of a second. And those failure processes start at kind of the micron scale, but can generate kilometers of deformation. And so to understand these systems, you need to be able to measure them at sort of a really incredible bandwidth in both space and time. In addition, they often occur in kind of inaccessible places, whether it's buried underground or dangerous places that are hard to instrument. And so direct observations are sometimes scarce or impossible. And lastly, they occur in very heterogeneous and complicated materials. And so sometimes that heterogeneity can be the dominant signal that you can measure, and it's hard to be able to kind of average that away or remove that signal. And so the goal of my research in general is to try to understand these systems with scale experiments that leverage techniques from applied physics and soft matter physics in particular, where the power is that they can scale your experiment down. They can kind of control those spatio-temporal scales and allow you to scale the experiment so you can put it in a lab. Usually you can make it transparent so you can directly access the kinds of information that you want. And ideally you can either build in or also measure kind of the heterogeneity and the complexity of that system. And so today I'm going to talk about how I've tried to approach that to understand faults. So I'll start by talking about seismological stress drops. Okay, so stress drop is one of the main ways we evaluate earthquakes. It's related to the seismic energy release and the frequency content of that earthquake, and it's usually interpreted as a change in frictional stress on a fault due to rupture. And it's calculated as a ratio between a moment and a rupture length cubed, or equivalently, sort of how is the energy dissipation scaling with the size of your rupture. The moment is usually estimated from seismic radiation, and the rupture length is calculated from a corner frequency of the displacement spectra, or sometimes it's estimated from aftershock area or geodesy. And one of the most sort of consistent observations about seismological stress drops is that they are magnitude independent, which I mean is this: as the rupture gets larger, as the moment increases, its rupture size scales cubically with that moment. And this has been shown to be true over almost 20 orders of magnitude, and it's been shown to be true for slow slip events as well. And so, but I will also note that, this is sort of, they're magnitude independent-ish, I'll just briefly note. And so if you look at sort of an individual data set, you might see that it doesn't quite follow this perfect constant stress drop scaling. And even over these 20 orders of magnitude, there's sort of a consistent 4 orders of magnitude difference in stress drop. Part of the reason for this is that stress drops have some issues with measurement. They're rupture model dependent, there are issues with measuring the corner frequency, and they can be difficult to measure for smaller events. Now, one of the other sort of interesting observations about stress drop is that they are largely invariant as a function of depth in the rust. And because normal stress increases with depth, this would indicate that stress drops are normal stress independent. Or are they? Okay, so our sort of basic fundamental theories for understanding friction, like slider block models and rate and state friction, would predict that you get linear dependence between change in frictional stress, as seismological stress drop that are interpreted, and the normal stress. And similarly, there have been sort of decades of experiments with linear independence between change in frictional stress and increases in normal stress. So what's kind of causing this disconnect between the stress drops that we see in nature and the stress drops that we see in the lab and in our theory experiments? And to me, there's sort of also a fundamental difference between the earthquakes in these scenarios also. Specifically that in nature, earthquakes are almost always occurring complex and heterogeneous faults. And in addition, in nature, there are almost always confined ruptures, by which I mean if you have sort of a fault patch that looks like a fault that looks like this, your rupture is contained within the bounds of the fault, and it's not reaching a free surface most of the time. By comparison, in the lab, faults are generally pretty homogeneous, and they almost always reach a free surface in either one or both directions. So in addition, you could also ask whether these two quantities are really actually measuring the same thing, whether seismological stress drop is really measuring changes in frictional stress. So the questions I'm trying to answer are sort of, are seismological stress drops normal stress independent or not? What causes the disconnect between sort of stress drop is measured in the lab and stress drop measured in nature? And how does it change our interpretation of stress drop as a seismological quantity? So since I'm talking to the computational geophysicist supposedly, I wanted to think about sort of ideal computational model to study this system. What kind of features would we want it to have? So ideally, you'd want it to be able to repeatably produce large numbers of events over many cycles of slip. You'd want it to be able to control whether you have system spanning ruptures or not. You'd ideally you'd like to be able to kind of get the sort of powers of computational systems, like measuring slip or stress across the entire interface, and direct control over parameters like stress, heterogeneity, and friction. And so what I'm going to talk about is, instead of using a computational model, using sort of a real experimental physical model that actually has all of these properties, but occurs in sort of a real physical system. And you might see that maybe there are ways in which that shows you things that are harder to measure in computational systems here. So this is sort of a schematic of our system. It looks a lot like a traditional biaxial friction experiment with shear and normal force on a top sample that's mobile against a sort of static lower sample. But instead of being made out of rocks, it's made out of transparent rubber called PDMS. So why should we use transparent rubber to study earthquakes? Well, I'll say 3 reasons. First is you can embed tracer particles just below this frictional interface. These little black tracer particles, and you put an opaque layer over it just for contrast. And what that means is that when this layer experiences deformations due to the shear at this frictional interface, you can image those deformations as displacements of the particles just below that interface. You can directly image displacement and velocity just below the frictional interface. Second, if you change the topography of this upper loading plate, for example, if you put a sphere that kind of protrudes into it, just like sort of the princess and the pea, if you're a very sensitive princess, you can feel that stress disparity underneath your mattress. Here, by changing the topography of the upper plate, you can locally create a stress heterogeneity or a stress disparity underneath this, based on the topography of this plate. And today I'm mostly going to talk about doing this with a single asperity directly in the center of the sample, but you could also do this with pairs of asperities or sets of asperities or any kind of complicated 3D printed surface you wanted to. And now last but not least is PDMS had about 50,000 times the compliance of a rock. And so this sort of 9 by 9 centimeter fault that we have in the lab is actually equivalent of about 4 kilometers on a side in the earth. And so we have ruptures that are almost exclusively confined within the bounds of our system. So we don't get surface ruptures in general. Okay, so here's what this looks like in real life. Here are these 2 fault slabs. There's this layer of sand in between, which I'll talk about in just one moment. We have shear and normal force, and we image it with a camera, a fast camera that sort of images through a mirror on the bottom. Okay, so here are our slabs. Here's that stress disparity pushing on the sample. So you have this, again, you have this thin opaque layer. In between these 2 layers are these embedded tracer particles. If you look through this transparent layer, so that's what you're seeing here, and then in a zoom in here, you can see all these little black dots. Maybe you can see kind of this sort of what looks like fine dust on the surface. And those are the tracer particles that you can image the deformations of, which I'll show you an example of in a moment. Now, in between the 2 layers, there's this sort of mono layer of sand across the surface here. And this sand serves a few purposes. First, it sort of randomizes the interface in between different experimental runs. So it creates this sort of local noise or heterogeneity or sort of randomness to your system. Second, it allows you to actually control the frictional properties of your system actively. So by in the current state where there's sort of a single monolayer of sand, your system is dominated by rubber on sand friction. If you increase the thickness of that layer, you're increasingly dominated by sand on sand friction. If you remove that layer, you're dominated by rubber on rubber friction. And in addition, it also acts to sort of deal with little imperfections in the casting process, which make those rubber on rubber experiments a little complicated. And I will note that the S-wave sees this experiment about 20 meters per second. The fastest slip speeds we can get on our system are sort of a quarter of a millimeter per second. And so we're really looking at just slow slip events in this system. So here's an example of the data you'll see. This is sort of an example data set. I'll play the movie in a moment, but here are all these tracer particles. And when I play the movie, if you look kind of in this center region, what we'll see is the sample gets loaded and then starts to slip. Okay, so if you kind of focus in the middle here, you'll see loading, and you can see these little deformations on the surface. And if I show you a zoom in, it's a little easier to see. You see this loading phase, and then all these sort of rapid deformations. And this is being dated about 4 times real speed. And so it's really just to show you that we can very easily image those deformations, not just kind of jiggling around like this. Okay, so we can then take this data and we can use particle image velocimetry, which is sort of a standard image autocorrelation technique, to calculate the displacement field at every time step in this movie. And with the displacement field, you can take a derivative and directly calculate the velocity at every location on the surface. And in this case, I'm mostly focused on the velocity in the sliding direction at every frame of this movie. Okay, so I'm going to play this movie in a moment. And what you'll see is this red dot is going to track the shear force through time. You'll see red represents sort of loading, blue represents slip. And what you'll see is that when I start to play it, you get this red loading that occurs, so it's big red patch. And then you'll start to see these flashes of blue that kind of pop into frame. Oh, sorry about that. And each of these sort of flashes of blue are an isolated slip event on our surface, these sort of isolated patch. I find this data a little hard to look at in its current form, so I think an easier way of looking at it is to look at 2 cross sections of it. So horizontal and vertical cross section, which looks a little like this, okay? So here's a sort of XYT data set. I'm looking at 2 cross sections in the direction of slip and perpendicular in the direction of slip. And what you'll see is you see these blue patches. These are sort of blue, these blue patches are these slip events that are occurring on your surface. You can see that they're somewhat correlated with these changes in the stress. And what we can do is we can take this full 3D data set and we can threshold it to isolate individual now blobs rather than patches in 3D space. And each of those blobs, those kind of bubbles, is an isolated slip event, okay? So here's one of these slip events here. And then for each event, we can calculate a range of parameters, a range of geometrical parameters like the rupture area, hypocenter, and centroid, velocity characterizations, but we can also directly calculate a moment by integrating slip across the entire event. And in doing so, we can kind of calculate a moment and a rupture area or a rupture length, and thus we can calculate a stress drop for every event on the surface. Okay, so first we're going to look at is how does the moment scale with the rupture length? And what we see is we get something that's pretty close to cubic scaling. It's not quite perfect, but I would argue that it's similarly imperfect to these other measurements of stress drop in natural systems. And part of the reason for that is that in this case, we also have to kind of assume some kind of rupture model. So in this case, we're assuming that all of the area contributes to an equivalent circular rupture. And so we calculate it as an area over pi square root of that. I'll talk at the end a little bit about how if we try to account for this sort of complicated shape, we can actually get a better cubic moment rupture length fit. But for now, even though we're getting slow slip events in our system, on this weird system that's sort of rubber on sand friction, we're getting earthquake-like scaling. And what we can do is we can now try to kind of use this like a numerical model and try to map out a phase space of behaviors and try to understand how as we change different fault parameters, what happens to that stress drop in our system. Okay, so what we'll do is we'll calculate a stress drop for each one of these data points, and we'll look at that distribution of stress drops. So I'm going to show you this plot, and we'll kind of build it out. But for now, I'll start with a simple example. So here is an example of a sort of homogeneously applied normal stress. And here is going to be plotted rupture length as a moment as a function of rupture length. So you have this cubic scaling. For each of these, you calculate a stress drop, and you can see that distribution of stress drop shown here. The average is this black dot, which is then plotted in the corresponding color here. And this is sort of the corresponding normal stress for this experiment, this set of experiments. And then down here is just your standard B value plot with 1, 1.5, and 2. B values of 1, 1.5, and 2 shown as kind of guides for the eye in black, blue, and red, respectively. Okay. So the first set of experiments we're going to do is apply homogeneous normal stress, and then increase the normal stress, homogeneously applied normal stress, and increase the normal stress, and see what happens. And what we see is that we actually don't get a change in the stress drop for increases in normal stress by about a factor of 8. Okay, which is kind of surprising, but is matching what we have observed in the Earth. Kind of interesting. Okay. Next, what we're going to do is now we're going to try to change the stress heterogeneity on our fault. So by adding in that central stress disparity, we're gonna increase the stress underneath it, and that's going to fundamentally change the distribution of slip on our fault. Okay, so if you look at this top row, this is the average slip at each pixel value, and you can see without the asperity, it's kind of well distributed broadly across the surface. When you have a central stress disparity, it's very isolated and higher underneath this sort of stress disparity. Similarly, the 90th percentile displacements are also kind of go from being broadly distributed to being isolated underneath the stress disparity. And if you look at the entire sort of ensemble of the data, you can really see that you're getting these larger slip events that are really isolated underneath the central stress disparity, as opposed to being broadly distributed for this no asperity case at the top. And in spite of this totally different distribution of stress, we actually see that we get a sort of indistinguishable stress drop that doesn't change as a function of normal stress, and actually doesn't change as a function of stress heterogeneity either. Quite weird. Okay, what about frictional properties? So as I said, we have this layer of sand here that's approximately a monolayer of sand. If we increase the thickness of that layer, we are increasingly dominated by sand-on-sand friction. If we remove the layer altogether, we're dominated entirely by rubber-on-rubber friction. If you measure the coefficient of friction for both of these things, they both actually increase the coefficient of friction. Sand-on-sand increases it by a factor of 2, rubber-on-rubber by about a factor of 8, and rubber also is much more cohesive than sand-on-rubber or sand-on-sand. And in spite of this, we see that changing doubling the frictional force, doubling the coefficient of friction, doesn't really change our stress drop very much. And increasing the friction by a factor of 8 only creates a sort of small change in the stress drop. But I will also note that there are a number of issues with these experiments, as you can probably tell from kind of the weirdness of this data. So I would take them with a grain of salt in terms of how much to believe them. Okay, so everything I've shown you so far is for sort of the largest fault samples that we've used. And in these large fault samples, what you see is that the ruptures are fully confined, by which I mean they are not rupturing to the edge of your system. So if you look at these ruptures, okay, these parts that have slipped, these kind of blue lines in space, you can see that they're bookended by areas of that are still under confinement or still under stress. And so our ruptures are sort of being confined within the bounds of this fault, and they aren't rupturing to the edge. So here's our fault, and here's our rupture. This is sort of a confined rupture. Now, what we can do is we can simply take our fault and cut it down to be smaller. And as it gets smaller and smaller, what you'll see is that more and more ruptures will reach the edge of your system. So we can directly test, finite fault effects or sort of confined versus unconfined ruptures in terms of their stress drop behavior. So when we make the fault a little bit smaller, we see sort of not really a real change in the stress drop, maybe a slight increase. But if we make it a little smaller still, now we start to see a sort of systematic increase in the stress drop as a function of normal stress. And if we make it even smaller, we see a very clear normal stress dependence and a large change in the stress drop. So these unconfined ruptures have a fundamentally different stress drop behavior than these confined ones. And just kind of to make it clear, if you look at the slip on sort of these, if you compare sort of a central asperity to this smaller sample, you can see here that it really is rupturing the entire sample surface. Whereas here, it's just predominantly located underneath the central stress asperity, but you can still get events that kind of are confined within the system, but they're more localized. These really are rupturing the entire interface, and that is what's causing this difference in the stress drop behavior. So to kind of summarize this part, confined ruptures, stress drops are independent of normal stress heterogeneity, largely independent of frictional properties. But for unconfined ruptures, we see an observed normal stress dependence that gets larger as you decrease the sample size. So let's kind of like bring this back to the question we're asking at the beginning, which is, why are stress drops for confined ruptures different than ones for, why are they normal stress independent? And why are they not normal stress dependent as we see in the lab? So we've recreated this observation of nature, this observed normal stress independence that we see for natural earthquakes, in a simple system in the lab that, again, doesn't have pore pressure fluidization, doesn't have cheating. It simply has an elastic fault and some stress heterogeneity, okay? But those two factors, those two ingredients, you can reproduce this normal stress independence that you see in nature. Now, the observations of changes in frictional stress as a function of normal stress have been a pretty robust observation observed countless times over decades. And so it's not like these observations are incorrect, right? So what's the disconnect here? What's really kind of driving this disconnect? And to me, the answer is sort of the simple one, which is that seismological stress drops, which take a ratio between a moment and a rupture length cube, and dissipation and size of your rupture, just aren't reflective of changes in frictional stress. And these two quantities should not be considered as representing each other. And the reason that we see this normal stress dependence for kind of unconfined ruptures is that as we increase the normal stress, our moment is going to grow, but our rupture length is going to be capped by the size of that sample. And so our seismological stress drop will grow with increasing normal stress. So if seismological stress drops aren't reflective of changes in frictional stress, the obvious question is, what are they reflective of? Okay, so let's go back and look at sort of this whole ensemble of slip that we're seeing on the fault. And what I've talked to you about so far is really just these sort of blue patches of slip. But you'd notice that there are all these red patches of fault also, which are essentially showing you the loading or the redistribution of stress. And you can think of this as sort of Coulomb stress transfer on this system. And what you see is that this process of stress redistribution is actually quite complicated. It's as complicated as the slip process itself. And so I'll just say briefly, like I'm now entering the speculation zone of this talk. Okay, take what I say again with a grain of salt here. But perhaps what this constant stress drop scaling that we're seeing is telling us is something about how that stress redistribution process works. That maybe if you have this ensemble of sort of large asperities and small asperities and kind of a broad distribution, as you load your system, your weak asperities will start to break. Those will load your strong asperities. Your strong asperities will break, which will load your weak asperities. And that redistribution process maybe drives your system towards something with stationary statistical properties that tell you how large of an event you will get given the amount of energy dissipation. They create weak patches that scale their moment as their rupture length cubed. Okay, so it's sort of, I don't like the term self-organization here, but something like a sort of self-organized criticality perhaps, or distribution of stresses. Again, speculation. This is something we're trying to work on to prove by actually looking at the dynamics of this process. Now, the last thing I'll say is this thing about moment rupture length scaling, at least on this part of the talk. if you look at this moment rupture length scaling for the different kind of fault conditions I described, as I said, they don't quite scale cubically. They scale a little below that, around 2.5. But for the confined ruptures, for the unconfined ruptures rather, you said they actually have more cubic-like scaling. And this is even easier to see if you kind of bin average all this data. You can see that these are actually scaling pretty well as moment and rupture length cues outside of this part where you get this large uptick. And so our thought was that maybe something about this confinement or something about the shape of this rupture is affecting this scaling. So for each event in this system, we calculated what's called a circularity. So a ratio between the perimeter squared over 4 pi times the area. And what that is circularity will be 1 for a perfect circle. And the less circular it is, the larger that parameter will be. And what we see is that for these unconfined ruptures, the circularity grows as a function of the size of your rupture. But for the confined ruptures, it maybe starts to grow, but then rapidly goes back to being more circular as a function of size. And that's because for these square and circular faults, where you're rupturing the entire sample, your rupture shape is going to be very square or circular as it's rupturing the entire interface. Whereas here, where it's unconfined, it's more reflective of sort of that complex stress state of your fault. And so it's more nebulous and lobed. And just as a note, if you look at the aspect ratio, you don't see that kind of scaling. You don't see that sort of difference between the confined and unconfined ruptures. And so the aspect ratio for almost all these events is pretty close to 1. So we're still equidimensional. It's not like you're getting more elongate ruptures. They're literally just getting more complicated and nebulous and sort of less circular, if that makes sense. So going back to this plot, what we tried to do was we tried to say, well, maybe there's a way of accounting for that non-circularity. And if we were able to kind of force this shape to be circular somehow with some kind of, characteristic parameter, maybe we could get improved moment rupture length scaling. And so the easiest one we could come up with is to look at what is the largest inscribed circle you can put inside this rupture shape, and then take the radius of that and call that the rupture length. And if you do that, you see a much improved moment rupture length scale. Okay. Now, I don't ascribe any particular meaning to this inscribed circle. It's just to say that if you can account for the shape of this, you do get improved moment rupture length scaling. And that, first of all, is true across all the different types of experimental conditions. But it also doesn't fundamentally change this stress drop story I told you earlier, where you get normal stress independent stress drops for confined ruptures and normal stress dependent stress drops for unconfined ruptures. So that's just a way of sort of accounting for these shape effects. So the main takeaways for this part of the talk, first of all, I hope you can see this experiment is a good system for studying stress drop, slow slip, and earthquakes in general. And to answer the questions I was talking about earlier, seismological stress drops are normal stress independent for confined ruptures. They are not for unconfined ruptures. The disconnect between lab and nature has to do with finite fault effects, geometry, but also how we interpret stress drop as being reflective of changes in frictional stress. And as I just said, it's really not reflective of changes in frictional stress, and maybe is instead reflective of how this stress gets redistributed and is along your surface over many successive slip cycles. Okay, so that's stress drop. Now I'll talk to you guys a little bit about some preliminary data we have on understanding earthquake nucleation. So going back to this plot, we have a ton of dynamic information on this surface, right? I was sort of reducing the system down into sort of a simple, just a moment and a rupture length, but there's all this information about sort of how these events grow and change through time, right? You could see how they nucleate maybe, and you can understand a nucleation process and how it's related to the stresses of the system. So a quick primer on earthquake nucleation. There are sort of 3 dominant models currently for how this works. One is this sort of self-nucleation or pre-slip model, where you have a slow aseismic patch that grows and eventually reaches a critical size, at which point it rapidly accelerates and starts to radiate seismic waves. And each of these sort of yellow explosions represents a foreshock. So in this case, foreshocks would be reflective of this aseismic growth phase. There's also this sort of cascade model where foreshocks are sort of small seismic events that trigger other seismic events and eventually trigger a asperity that is critical enough that you generate a large seismic event that rapidly accelerates. Now, recently, Greg McClaskey has sort of proposed this additional model where it's sort of a combination of these two, where you get this slow aseismic growth, but eventually that triggers slip on sort of a critically stressed patch of the fault. And this is related to this idea. This has also been sort of described as migratory nucleation, which has been observed in Willem's ice sheet. So each of these colorful dots are a GPS station, and this purple star is a ice quake that occurred here. But if you look at the GPSs leading up to this ice quake, you can see that on this orange station, the slip actually started on this orange station before you generated an event here. So the event started all the way over here and migrated here and triggered an event there. This is sort of this migratory nucleation idea that people have been talking about. And buried in these questions is sort of the simple question of, do slip events start where the stress is highest or not? Are they starting underneath asperities, underneath high stress patches, or are they starting elsewhere and kind of migrating towards those stressed areas? So let's look at an event on our fault. Okay, so this is the event that you're looking at, sort of the projected velocity perpendicular to the direction of sliding. So this is the direction of sliding. This is time. And I've only isolated the event itself. So everything else I've set to 0. And if you were to identify sort of the hypocenter of this event, it would be here. Okay, so here's the hypocenter. Now you might notice that if I were to pick, say, a different threshold for this event, you might get a different hypocenter. Okay, so some of what I'm telling you is a little bit threshold dependent, but again, this is preliminary data. We're trying to kind of quantify the role of thresholding in this system, but just for now, let's look at this hypocenter. So you can identify the hypocenter for this event. You can identify the portion on the fault where it is slipping the fastest, so the location of fastest slip. And in addition, if the experiment is an asperity experiment, you can also locate the location of the asperity. Okay. Now, this is the same event projected in the time direction. And here now you're seeing the hypocenter, that highest slip speed point, and the location of the asperity for this event. And what you might see is that these are not the same point. Okay, first of all, at least for this experiment, for this particular event. So what we can do is we can measure the location of each of these points. We can measure the distance between them, and we're also going to measure the angle here between these 2 points, the angle between the hypocenter and the highest slip speed, and the hypocenter and the asperity, because that will essentially tell us that as the event nucleates and accelerates towards the highest slip speed, is it doing that in the direction of the asperity or in some random direction? So we're going to look at this for 3 different experiments. First, one where there's no asperity, and you can see the slip is kind of broadly distributed across the fault. Second, where there's a central asperity, and that asperity is, you can see the slip is predominantly distributed underneath it. And then a third experiment where we have the same height of asperity, okay, so the same protrusion, but we've made it twice as wide. So sort of a wider asperity here. For these 2 experiments, we can locate the asperity at the beginning and the end and assume it moves linearly between the 2 locations throughout the course of the experiment. So we know the location of the asperity across all time points. And for the no asperity case, these were sort of a central asperity on the fault. And so we can also locate the center of the fault and consider sort of the equivalent asperity location to compare everything across these 3 experiments. And when we plot the hypocenters for all of these experiments, okay, hypocenters are shown in black. The green dots are sort of the hypocenters that are above a threshold, so sort of the largest event on our system. what you can see is that the hypocenters are not occurring sort of just underneath the asperities. Maybe they are reflective of, if you took the ensemble average, that would tell you something about where the asperities are, which is itself kind of interesting conclusion. But they're generally not actually occurring directly where the asperity is. And so we're going to try to quantify the distances between these different points for each of these events. So the large asperities at the top, the central normal asperities in the middle, no asperity at the bottom. And what you can see is that you get the largest sort of peak in the moment and the largest number of events occurring sort of a few millimeters away from your asperity. So not underneath the asperity, but away from it. And then you get this sort of fall off away from that. Whereas on the homogeneous fault, homogeneously applied normal stress, you get a sort of broad distribution of events, as you might expect. You can also look at these as histograms rather than as a function of moment. And you can see that, again, these sort of modal hypocenter to asperity distance is not 0. It's sort of a few millimeters. And it increases with the size of your asperity. Okay, so your hypocenters are starting further away from your points of highest stress, the larger your asperity is. The same is true of your max velocity point. That is also not happening where the stress is highest. And the hypocenter and max speed point are closer, but also not the same location. So essentially, the hypocenter, the max speed point, and the asperity are 3 separate locations that are more distant from the asperity with increasing asperity size. And if you look at this angle, okay, you can see for the non-asperity case that it's sort of broadly distributed, sort of -60 to +60. So 0 would be they're kind of directly in line with each other. And as you increase the size of this asperity, you get almost increased kind of focusing of that angle. And so what this tells you is that events kind of nucleate away from the asperity, they accelerate in its direction, and eventually kind of slip your fault patch. And so this is sort of consistent with this migratory nucleation picture, where you get this slow aseismic slip that travels and eventually ruptures a large patch. So in conclusion, these scaled experiments are sort of a powerful tool where you can do almost modeling-like experiments and measurements. And with that, I'll just take some questions, I guess. Thanks.